student actually from the United States, from Brigham Young. So I'm very grateful for this opportunity to be here to present to you today to the Organic Phosphorus Workshop. It's been a lot of fun so far. So we're going to be looking at the phosphorus mineralogy, chemistry, and speciation Utah Lake, which is in the western United States. I'll show you a little bit where that is, but this is an image taken of that area, very pretty area. Just as a preface, so I'm a geologist. I kind of am a little bit different than the rest of you. I feel like this black sheep here amongst all these organic phosphorus experts. So I hope for advice after what I explained to you, and I hope that you can come to me and tell me what I'm doing wrong and what I can do better. So Utah is located just right here, and I'm going to be looking at Utah Lake. So the Great Salt Lake, it's about a 45-minute drive south of the Great Salt Lake. It's a natural freshwater lake that feeds to the Great Salt Lake. This is a Google Earth image of Utah Lake, and to give you some characteristics, there's about 500,000 people that live just along Utah Lake right here, and the lake is a very shallow lake. It's only about 2 meters deep on average, with the deepest part being about 3 meters, so not very deep, and it's a very calcite-rich lake. The majority of these mountains are limestone, so we get a lot of calcium carbonate coming down from the runoff. And it also has a little bit of silica. There's some quartzite that's just running along the edge here. So it's a very calcium-dominated lake along with some silica. Due to its very shallow qualities, whenever wind comes, which is quite often, the lake is basically generating a lot of these total suspended solids in the water, which reflects a lot of light. And a lot of people think that it's actually light limited instead of phosphorus or nitrogen limited. And whenever the wind blows, everything's below wave base, so it just a lot of sediment, which is mostly really fine-grained particles of mud. You actually sink to your knees if you step in, so not fun. And this right here, which we'll be talking about, is Provo Bay. It's a lot higher phosphorus due to the amount of sewage plants discharged into the lake. And it's much shallower. It's only about 3 centimeters, so very shallow. Recently, 2 months ago, we had a bacteria algae bloom. This is one of the state parks where people are boating, and this algae bloom is about a mile long. It's the first time in Utah Lake's history that they actually had to close the due to this harmful algae bloom. And I have kind of I don't know if you can see it very well, but this is just a time-lapse video of that algae bloom actually entering into the bay. And so it's been quite a big problem in the area. A lot of people have really become worried about this issue. And so, of course, they closed the lake. They put up signs showing and the news went nuts over it. So, I mean, Fox is in the news, but usually bad things. So, and that's what I deal with. So, got a lot of people talking to me about that. Part of this issue is because we have 7 sewage plants that discharge into the lake, and none of them are currently regulating the amount of nitrogen or phosphorus coming out of the plants. So that's mainly why we have so much phosphorus in the lake and get these algal blooms. They're currently discharging about 3 milligrams per liter of phosphate in their effluent. And the Division of Water Quality to try to bring it down to 1 milligram per liter, which is going to cost the local area a lot of money. And I really don't think that will make a big difference to the lake to limit it to 1. So we're looking for a better way to just limit it to 1 milligram per liter. So this is a very basic diagram, and I'm mostly just interested in this part, being a geologist. Probably a lot more that's missing over here. Basically, we have a lot of wastewater effluent coming in. There is irrigation around the lake down here, and we get a lot of irrigation runoff that comes into the lake. So I'm mostly interested in the phosphorus that's settling into the sediment and possibly being resuspended during these wind events or if a boat propeller goes by. Some people do boat in the lake, not very many. Usually it's very, not a lot of people are there, basically. And so the questions that I'm going to be looking at are, I wanted to look at what is the fate of phosphorus, where is it going into the sediments, and then subsequently, what is the mobility of that phosphorus after it reaches the sediment? And so are we seeing absorption, or is there actually mineral precipitation that's going on that's making it unavailable to the biology? Some of my methods, I collected 9 samples on the lake, both samples and surface and pore water samples. And then under the water analysis I ran on the ICP, and I also did some samples. And mostly I was looking at the sediment using XRF and Electron microscope images, batch sorption tests, sequential leaching to try to figure out where all this phosphorus was. So this is a boat that I got to use because 3 centimeters is good for a boat or a canoe. So airboat's really the only way that you can get out there to get these samples. And those are kind of the sampling sites that I've just started, so I don't have all of these sites yet, but I do have some preliminary results for you. And I want to get, the first question that I'm asking is, what is the fate? So we see that from my preliminary data, dissolved in particulate phosphorus. The way that we say dissolved, or that phosphorus is dissolved, filtered through a 0.45 micron filter, we consider. And so you can see that in at least an area where all the treatment plants discharge, there's another treatment plant discharging here. We get much higher concentrations of phosphorus in the surface water, of about 4 milligrams per liter, whereas the rest of the lake is about 5 milligrams per liter. And it kind of varies in between how much is particulate and dissolved. It doesn't really look like there's any particular area that's either dissolved or particulate. Is different throughout. And looking at the water, we find a little bit higher concentrations. Again, see where the treatment plants discharge, we have higher concentrations of phosphorus in the pore water, reaching up to 5 milligrams per liter, whereas the rest of the lake is only about 0.5 milligrams per liter of pore water. So now we want to look at some XRF data. This is X-ray fluorescence, and we were able to find that silica and calcium, which we guess because of the geology, sort of dominate the sediment, as well as we do have about roughly 20 to 25% organic matter, which we have found through a loss on ignition. We do have some aluminum and iron, which has been known to with phosphate and phosphorus, and then that kind of makes up we have a lot of iron sulfides and then some clay minerals. This is electron microscope images of the sediment, and I've labeled each element as sort of one of these different colors, so you can it's hard to see the phosphorus in this, but it's blue, and most of it is distributed throughout the grains, showing that it's not particularly absorbed. Just one grain in particular that we can see at this point. It's mostly just disseminated throughout. I mean, you can see some aluminum-rich and showing clay particles, and then you do get some hot spots of some sulfides. Sorry for the here. I was trying to figure things out, and I couldn't get it to work, but the same end up seeing in this that this is in the Bay Area of Utah Lake, that we do find a highly concentrated phosphorus region right here, which we'll talk about later. So absorption results, I took some lake water and ended up putting some sediment in it, some lake sediment, and spiking it with various levels of phosphorus to see kind of what our trend was and how much the sediment could hold. And we found that it's a very linear trend. Even at 300 milligrams per liter of phosphorus, the sediment is still a lot of this phosphorus in the water. So there's a capacity of the sediment to hold phosphorus. Now moving on, we want to know more about the mobility of this phosphorus. Is it going to be phytoplankton? It's as the wind comes by and resuspends a lot of this sediment. I've done some sequential leaching and extraction tests to find that most of the phosphorus is either bound up with these iron manganese hydroxides or this apatite. Calcium, there's a lot of calcium, so it could be calcium carbonate, or we could be seeing actually hydroxyapatite precipitation. And so these went through and did, these are my extraction methods it looks kind of similar, I guess, to soil extractions that we do. This electron microscope image, and I really like it because you can see this pyrite grain. Geologist, so it's an iron sulfide. We're going to look very particularly this grain here, which we've already had a great picture of an apatite from Mark, but this is actually an apatite grain, which we zoom in on, and we're able to use the electron EDS and WDS to find that you look at certain elements in specific and find that it's very calcium, phosphorus, and oxygen rich, which is the structure for. And so this is only, I don't know, 4 microns and about 2 in width, but we do find similar crystals. This is just one of the best. And I did some really quick geochemical modeling and found that so any above 0 is supersaturated and has the potential to create hydroxyapatite, and anything below 0 is undersaturated and has the potential to dissolve apatite. So we are seeing a really potential in that bay area, but throughout the rest of the lake, not so much, and maybe the potential to dissolve. So in conclusion, I found that apatite is in Utah Lake, and it has the potential to be precipitated, which would make it not very bioavailable plant use. However, there is a lot of to redox-sensitive iron and manganese, which during the event might be oxidized after being and releasing a lot of that phosphorus that has been absorbed. There's high amounts in the pore water, and some in the could also be released during these storm events. And the mobility of phosphorus, I haven't done much with yet, but I have a lot more samples to come, but that roughly 40 to 50% is potentially mobile during windy events, but that 60% is bound to apatite or calcium carbonates, which would make it mobile. And I would just like to acknowledge my funding. I am funded a lot by these treatment plants, so put that up there.